think so.
It's just emergency rescue. That has to be really confirmed. Huh? Where's it?
Still keep flying. That's good, yeah.
They were like dealing with patients or something.
Yeah, take disability.
Finding like a freaking.
They had like there's like people in like South.
Shit, like real
Like
Yeah,
people, yeah.
yeah.
Yeah, they're freaking finding prosthetics for them.
Yeah, but one of
It's
the
legit.
people already done it before.
That project sounds like legit.
Yeah, it's like a real country that has to work.
It's for
It's a lot of pressure.
It's for like an actual person.
Yeah, that's a great. And they have to choose like who they have multiple.
I feel like mine is like whatever too. It's for the Arboretum, the children it's crying. Oh, it's for them to like learn about conservative energy. So, sure, yeah, that's the part of it.
Yeah, well,
Like research a lot. That would come up with solutions. Right, so that's creating something. So I'm thinking now, like, I was also thinking, what I was thinking, like, they said it's gonna be around like kids, so like, what if it like hits them or something?
Make it sharp so they don't.
That's the thing, yeah.
And if they do, like, they'll learn the lesson.
That's really challenging.
That's like.
Some of it, I didn't finish it. I think that's like, yeah, but then
it's 30,
Yeah.
37, 34, 37.
Well, that's pretty.
Per day.
Shake A and B. There's no issue there. There's like need more.
Yeah, but I think it's cool.
Yeah.
I would just keep it.
That's what I
If
would-
you're out to my plan, just.
That's what I
Try this.
Sure.
For ignorant purposes, you know.
Yeah.
And no vibration, that's what we're saying.
She was.
Look at that.
She's looking great. Should be like an.
The front door, open the door.
All right, it's 4 o'clock, so let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, doing good. End of week 5, and so probably you guys are having midterms coming up, so I know things are gonna get busy real soon. All right, so the plan for today is we're going to be continuing on with our series on static biomechanical analysis. And so on Tuesday, we started reviewing the lower extremity. And so we talked about kind of the general characteristics. We went over the bones, the muscles. And so today we're going to do some example problems of static biomechanical analysis on the lower extremity. Okay. Okay, and so that's about it. And so I think the homework's due soon. So I know people have been working on that. So if you have questions, don't be afraid to reach out, either by email or you can come talk to me after class. Okay. And so are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. All right, and so let's start talking about lower extremity static analysis. Okay. All right, and so just like we talked about on Tuesday, what sets the lower extremity apart is that it's a large part of its responsibilities are in weight bearing, supporting the weight of the body. Okay. Okay. And so that's unique compared to the upper extremity, which does almost no weight bearing at all, right? And so as a result, a lot of the bones, a lot of the muscles, just a lot of the joints in particular are built just a lot more stoutly than the upper extremity. Okay? So you're gonna have bigger bones, bigger muscles, and just overall bigger structures. Okay? So a lot of the examples today have to do with kind of this weight bearing, and so we're going to do some examples regarding to that. But I want you also to remember that the lower extremity also has the unique responsibility of locomotion, right? And so when you need to get from point A to point B as a human, most times you're going to rely on your legs to do so. Okay? And so what you'll see is that the amount of forces that the lower extremity has to endure, both in terms of how much forces the muscles have to produce and how much reaction forces that occur at the joints are very, very high. I think a lot of people are pretty surprised to see, what kinds of forces the lower extremity has to do. But that's because it has these two responsibilities. All right, so let's start with a simple example. So let's do an example where we look at the hip joint under the usual stress of someone standing up. Remember the hip joint consists of the head of the femur as well as the pelvic bone. Okay. And so it looks a little something like this. And so we have the femur with its femoral head. Just like that. And that rests inside the pelvic bone, the pelvic cavity. Something like that. Okay. And then what we're going to assume is that the weight of the person is acting down over here. Okay, so we'll call this WT. Okay. And so I think when most people think of just standing, if you stood up here or if you stood up kind of in your seat right now, I think most people think of standing as a largely passive, passive activity, right? And so you're just kind of standing up, and it feels like you're not really doing anything active to support your standing. But what's actually happening is that there's a lot of your core muscles and a lot of the muscles in your lower legs actually have to be actively engaged to make sure that you remain standing straight and you're remaining stable. One muscle in particular that I think a lot of people don't think about are your hip abductor muscles. And so your hip abductor muscle is kind of attached from your pelvis down to your upper thigh. Okay. And so the reason your hip abductors have to act is because, if they don't, they kind of play the role of kind of holding your body kind of together from the lateral side. Okay. Because the natural tendency to do is that, because of the shape of the femur and the fact that it kind of points kind of more outwards, if you kind of just let it sit there on its own, the natural thing is for this to kind of just pop out of its place just like that. Okay, that's just kind of just how it's designed. And so the hip abductors are there to kind of make sure that the femoral head kind of stays in place. Okay, and so of course, if you're standing up and you're supporting weight, you also have a reaction force. Okay? And so call this force J. And for this problem, just because I want to keep it simple, we'll assume that we know the direction of J. And so we'll say the theta angle here for J is 75 degrees. And then let me put the angle for the muscle force too. So we'll say that the muscle force angle here is 70 degrees. Okay. And so very similar. And so they're going to be almost parallel, but not quite. All right, and so just like we normally do in these kinds of problems, we're looking to solve for the muscle force and the joint reaction force. Okay. But in this particular problem, we only have two unknowns. Okay, so normally we have three. And so I think a lot of you are working on the homework problems. You know that normally we have three unknowns, right? So we have the muscle force as well as two components of the joint reaction forces. Okay, here we only have two. And the reason we only have two is because the direction of the joint reaction force is actually given here. Okay? Okay. So that's an important distinction I want to, I want to make aware for you guys. So most of the time, you're going to solve for two components of the joint reactions. But if you're given some information about it in terms of its direction, then that cuts down the number of unknowns by one. Okay. And so since we're given the direction of this hip joint reaction force, then we only just have to solve for the magnitude of J as well as the magnitude of Fm. Okay. Because again, because Fm, the direction is given to us. And so we know what the angle is there. And so we just have to solve for the magnitude. Okay. Okay. And so that makes things a bit easy for us because then we don't actually need all the equilibrium equations. Okay? And so we only need two equations. Right, and the two equations I'm going to use are the sum of the forces in the x direction and the sum of the forces in the y direction. Okay. Right, so let's do the sum of the forces in the x direction. And so we have J. Okay. And so J here is pointing up to the right. And so, we're going to give it a positive sign. Okay. And then we only need the x component of it. So we're going to do J cosine theta. Fm, on the other hand, is pointed down to the left. And so that's going to be a negative x component. It's a minus Fm cosine. I'll call this theta m right here, just to distinguish it. Okay, so it's going to be a minus Fm cosine of theta m, where theta m is 70 degrees. Okay. And so we're going to repeat that process for some of the forces in the y direction. So the y component of the joint reaction force is J sine theta. And it's positive because J is pointed up to the right. A question, wouldn't it be easier to use the moment equation? We'll straight up get one value from that equation alone. That's true. You can do that too. But the moment equation is a bit difficult to use here because we're not given any of the distances. And so remember, if you're going to use the moment equation, you need to know what the lever arms are. And you can certainly measure that in a certain person, but for this example, we're not given. Yeah. Okay, and so we need the y component of the muscle force now. So we have a minus Fm sine theta m. Okay. And we also have the weight as well. And so we have a minus Wt is equal to 0. Okay. Okay. And so we have two equations, two unknowns here. And unfortunately, we don't have one equation that just lets us straight up solve for the other one. So we're going to need to do a substitution method. So let me go ahead and grab this equation here. Okay, this one's a little bit easier to work with. And so from this, what we get is, let's go ahead and solve this equation for Fm. Okay. And so if we move Fm cosine theta to the other side of the equation, we divide both sides by theta m, we get Fm is equal to J cosine theta m then what we can do is we can then take this answer and plug it into the second equation. Okay, so this is kind of a substitution process. And so if we plug that in, we know it's the sum of the force in the y direction. We get J sine theta minus J cosine theta m times sine theta m minus WT equal to 0. Let's go ahead and solve this for J now. So what I'm going to do is I'm going to take WT, move it to the other side of the equation, and factor out J on this side. And so we have J sine theta minus cosine theta. Okay. Then we have sine theta m divided by cosine theta m. And so that's going to be tangent of theta m. Right? And all this is equal to WT. Okay. Now let's divide both sides by this factor here. And what we get is J is equal to WT divided by sine theta minus cosine theta and theta m. Okay. Let's plug in the numbers from the problem. And so we know theta here is 75 degrees. We know theta m is 70 degrees. And then WT, I think I forgot to give you WT. WT we'll assume is 300 newtons. Okay. A somewhat arbitrary number, but I think I chose this to match the weight of a typical person or a typical child. I don't remember. Okay, and so we plug all that in, and we get a joint reaction force of 1177.3 newtons. Okay, and so our hip joint on just one hip, by the way, is experiencing a reaction force of that magnitude. Okay, so now let's plug this back in and compute FM, because what we know is FM is equal to J times cosine theta divided by cosine theta M. Okay, so FM equal to J cosine theta divided by theta M. Okay, so J we just solved for. J is 1177.3, and so we divide and we multiply that by cosine of 75 divided by cosine of 70, and what we get from this is 890.91 newtons. Okay. Any questions on how we got these results here? Okay. All right. And so let's break this down a little bit. And so let's take a look more carefully at these results. Okay. Throughout this analysis, we assumed that we had a body weight of 300 newtons, right? What we see from our results is that the muscle force, the one muscle force that we're considering here, has a magnitude that's almost 3 times as high as the body weight. Our muscle force is almost 3 times as high, but our joint reaction force is almost 4 times as high as that. Right? And remember, we're not doing anything special. This is just someone that's just standing up. And so me standing up here, at this podium, my hip abductor muscles and my joint reaction forces are sustaining, huge amounts of force. And so I weigh close to about 160 pounds. And so my hip abductor muscles are probably outputting somewhere on the order of almost 500 pounds of force, whereas my hip joint is experiencing a reaction force of almost over 600 pounds. So, it's quite a lot. And so once you start putting, real numbers on it, it starts to get, pretty large. And so you might be wondering, is this, that can't be right, right? And so, for just a simple free body diagram like this, we did apply quite a few assumptions to this. Like we assume that there's only one muscle that's going on. We assume that this person's a pirate and doesn't have another leg. And so, most people aren't like that. But, a lot of laboratory tests actually confirm, maybe not to this degree, but they confirm that, a lot of the muscle forces and joint reaction forces do experience very, very high loading. Okay? Okay? And so, for example, a lot of measurements have been taken of people doing just normal walk. Okay? Right. In a few weeks, we'll actually see that walking is actually very passive too. So actually, you don't have to do much active thinking during walking. But even during walking, what scientists have found is that the compressive forces in the hip joint range anywhere between 240 to 260% of the person's body weight. Okay? And that's on an individual hip joint. Okay? And once you ramp up the activity, the reaction forces will grow even more. So during running or jumping, people, what scientists have found that the hip joint can be under stresses that are anywhere between 420 to 860% of the body weight. Pretty significant. And so your hip joint's doing a lot of work, even when you don't think it's doing well. All right, any questions on this so far? Okay. All right, so that's for a normal hip, but a lot of people don't have perfectly healthy hips. And so let's consider a case when someone has injured their hip. And so in severe cases, when someone's hip is particularly compromised, then oftentimes they have to support their weight with a cane. Okay? And the idea with the cane is that, to offload some of the weight from the person's body onto the cane, so the hip joint and the hip and the muscles around the hip don't have to work as hard to support the body. Okay. And so a question that a lot of people have is that, if you're only injured on just one side of your hip, so let's say that you've injured just your left side, then should you, and you're going to use a cane to support yourself, should you put the cane on your left side or should you put it on the right side? And so should you put it on the same side that you're injured on, or maybe the opposite side? And so to answer that question, let's kind of take a broader look at what your leg and your hip is doing when you're kind of walking normally. And so during normal walking, and you can watch someone walk, to kind of confirm this. There's a part during when you're walking when one foot is swinging on in the air, right? And so you're basically only supporting yourself with one foot. Okay. During that stage, you kind of naturally shift your body weight so that your center of gravity is kind of right above the foot that is being planted. Right? Okay. And so I think, visually, I think people see this the most when you see like a fashion model kind of walking down the catwalk, right? And so they kind of, swing their hips a certain way to make them seem more attractive. But actually, normal people actually do that too. It's just that, it may not be as obvious. And so, during a certain part, when you just have one foot planted on the ground, the other foot swinging, your leg actually looks kind of something like this. And so you say this is your thigh. This is your lower leg or your shank, and this is your foot, okay? And this line right here, and we'll say that this line here is the, the line where there's your center of mass acting, okay? And so we'll say that it's the midline of the body. You're at a certain point when your leg is kind of out there, kind of like that, right? And so you kind of almost have like a leaning tower of Pisa kind of. But we know from the previous example that this leg here has to stay attached to your hip. Okay, so your hip, it's like right here. Okay. And so to do that, we saw from the previous example that there is a muscle that kind of comes off the side of your leg like this. Okay, so this right here is your hip abductor muscle. And that hip abductor muscle has to act to basically make sure that your leg stays in contact with it. Okay? And so this hip abductor muscle is contracting, and so it's producing a force, kind of like that. Okay? Right? And as you can imagine, when you're in a stance like this, the hip abductor muscle has to push pretty hard. It has to work pretty hard in order to keep your body upright. Okay? And so the idea with walking with the cane is to kind of adjust your stance when you're walking so that your hip abductor muscle doesn't have to work as hard. Okay? And so actually, the better way to use a cane is actually to put the cane on the opposite side of where you're injured so that the cane can kind of help relieve some of the stress. Okay? Because the idea is that if you put the cane, let's say that you put the cane over here. Okay? This is a cane, it's not a peg leg, it's not a pirate peg leg. Okay? And so the idea with the cane is that you shift your some of your weight onto the cane. Okay? And as you shift the weight onto the cane, then the midline of the body can shift to the right as well. Okay? And as you shift the midline of your body, then your leg doesn't have to be as slanted. Okay, so your leg kind of straightens up. Okay? And then as the leg straightens up, then that lowers the amount of stress that the hip abductor muscles have to, or it lowers the amount of force that the hip abductor muscles have to output. Okay. Okay. And so let's put some numbers on this and let's put an actual diagram on it to kind of help with that. Okay. I know I said I put an example up there, but this is the actual example. Okay. Okay. So let's go ahead and put the cane on the opposite side. Right? All right, so let's see, we have a person's leg just like this. Okay. And we'll say that the person's weight is being applied upwards right here. And so we'll say that the force has a magnitude of 200 newtons. Okay. Meanwhile, the cane on that side is going to support 50 newtons of weight. So you basically shifted 20% of your weight onto the cane. Okay. And because of that, the midline of your body is kind of over here. Okay. Okay. And so of course, we still have our hip abductor muscles. And so if we go right here, okay, that's our hip abductor muscles. And so just like we did in the first example here, we're going to compute the muscle force. Okay. The muscle force associated with the hip abductors, as well as the reaction forces at the hip joint. Okay. Any questions on this so far? Okay. All right, so let's go ahead and let's draw a free body diagram because the diagram we have now is not conducive for that. Okay. All right. All right, so I'm going to imagine the leg as kind of one single rod. Okay. And I'm drawing it a little bit exaggerated. And so, normally the slant isn't this much, but it'll help with just clarity of the drawing. Okay. And then I'm going to make a little bit of a turn right here. Okay. And so that turn there is meant to represent the femoral head. Okay. And so this point right here is, this part right here is the head of the femur. And so that's the part of your thigh bone that connects to your pelvis. Okay. Okay. So let's start labeling this this figure. So let's start with the muscle force. Okay. And so the muscle force is acting just like that. Okay. And so your hip abductor muscle is kind of attached to the kind of the pointy part of the thigh. And so the part below the head, so we'll call that the femoral neck. Okay, so it attaches the neck, not at the head, because the head attaches into the bone. Okay. And the joint reaction forces are going to be acting at the head. Okay, so we have J, Y, and we'll say JX in this direction. So I'm gonna erase this label here for femoral head just so I have some room, because it's about to get a little bit messy. Okay. Next thing we want to do is we want to know the direction of the muscle force. And so this angle right here, and so we're going to assume that we're defining this angle with respect to horizontal. We'll assume that this angle right here is 70 degrees. Okay. And we also know this horizontal distance, and so we'll call this LM. Okay. And we also know HM. Okay. And so this will actually be the first time that, because the muscle force is not acting, within a horizontal line or a vertical line of the joint, what you'll see in our moment equation is that we're going to need both. We're going to need both the vertical and horizontal components, because they're both going to contribute to the moment. Okay. And so that's why I've defined both of those, LM and HM. Okay. So LM being the horizontal distance between the muscle attachment and the joint, and HM is the vertical distance between the muscle attachment and the joint. Okay. So there's quite a few variables here. And so I want to make sure I define all of them well. Okay. And so next we have the weight of the leg. Yeah, I'm gonna move it to the left just a little bit, just to make the drawing a bit more clear. But you can keep it in your figures, okay? Because this W leg is also going to contribute to the moment. And so we need to define this distance here. And so we'll call this distance LL. Zoom in. Okay. And so the horizontal distance between the weight of the leg and the hip joint, we'll call that LL. And then finally, we have the normal force from the ground. And so we'll say the normal force from the ground is 200 newtons. Okay. And since we're going to need to compute the moment from the normal force from the ground, we also need the horizontal distance. And so we'll call this LF. Okay. Let me go ahead and start defining these parameter values. And so we'll say LM is 7 centimeters. LL here we'll say is 6.5 centimeters. LF is 5 centimeters. W leg here will be 50 newtons. And HM will be 1 centimeter. Okay. All right, so a lot going on, but you'll see once we start writing the equilibrium equations, it'll all kind of fall into place. Okay? There's just kind of a lot of parameters to go around. So I want to make sure I go over that carefully.
Are we going to include the cane?
So we're just looking at the leg, and so the cane, we're assuming that the cane is offloading 50 newtons of force, and so we're just looking at this leg. And so the idea is that because of the cane, then this force right here is a lot less than what it was before. Yeah. Okay. All right. Yeah. So I know it's a lot, but it's that's kind of how it is with a lot of parameters. Then there's kind of just a lot of things to go off of. All right. And so our knowns in this case are FM, JY, and JX. Okay. And so we're going to solve for them just like we normally do through the equilibrium equations. Okay. All right. And so let's go ahead and we'll sum all the forces in the x direction. Okay. And so that some of the forces in the x direction most of the time are going to be pretty straightforward because a lot of the forces we consider are just weights. Okay. And so here our only x forces are going to be coming from the muscle and from the joint reaction forces. Okay. And so what we have is a positive FM cosine of 70 degrees minus JX is equal to 0. Okay. Now let's go ahead and sum up the forces in the y direction. And so in the y direction, we have FM sine of 70 degrees plus JY minus W leg plus 200 newtons. That's equal to 0. Okay. And then finally, we have the sum of the forces around the hip joint. Okay. So let's go ahead and do that. And so remember, the reason we're summing up the forces, we're summing up the moments around the hip joint is so that we can eliminate JX and JY from those equations, and we can just solve for FM straight up. Okay? But remember, this one's different because, because we're given FM in this direction and we're given the horizontal and vertical distances, there's actually going to be two components of FM that need to make it into the moment equation. Okay. So let me show you what I mean. And so first, let's take the vertical component. And so we have FM sine of 70 degrees. Okay. And so that right there is the vertical component of the muscle force. And so the vertical component, we're going to multiply by the horizontal distance. Okay. Right, and so we have FM sine of 70 degrees times LM. Okay. And that's positive because that force is going to try to rotate around in the, I'm sorry, it's negative. Okay. It's negative because that force is going to push a clockwise moment around the hip joint. And then we have the horizontal component. So we have FM cosine of 70 degrees. Okay. And so that right there is the horizontal component. And then we're going to multiply that by the vertical distance or the vertical moment arm of the hip joint relative to the hip abductor muscle. And in that case, we make it positive because remember the origin of the force here is kind of on the bottom left. And so if we take a horizontal line and we go this way, right? So that's the horizontal component. We see that that's going to push it in the counterclockwise direction. And so the vertical component has a clockwise moment, but the horizontal component has a counterclockwise moment. Okay. All right, and so from here, we're just going to add the components from the weight of the leg as well as the normal force, at the bottom. Okay, and both of these are going to be positive. And so we have W leg times LL plus 200 newtons times L. And all that's equal to 0. Any questions on how we obtain these equations here? All right, and so from here, it's just algebra. Oh,
sorry.
question?
Yeah, shouldn't both components of FM be negative because they're both pushing to be clockwise?
So the horizontal component is actually going to be positive. And so let me kind of draw a bigger picture here. And so here is the hip joint, and kind of here is the point where the force is acting. And so it's kind of acting in this direction right here, right? Approximately. And so if we take the vertical component of it, this one's absolutely clockwise. And so if we take this like this, and then this right here is the pivot. And so it's going to go around this way. Okay, so that's clockwise. But if you look at the horizontal component, it's coming this way. And remember, you have to think about where it's acting relative to, the joint. And so since the joint here is in the upper right, if we kind of follow this around, it's going to go that way in the counterclockwise direction. The reason for that is because the muscle force is kind of pointing towards the joint as opposed to away from it. And so when the muscle force is kind of pointing towards the joint, you're going to have one component in positive, one component in the negative direction. Mm-hmm. All right, so let's go ahead and solve these equations. And so we have, just like we normally do, we have the moment equation where we can solve for FM straight up. Okay. And so if we do that, we get FM is equal to 212.48 newtons. Okay. Okay. And so that's of course, I skipped a couple of steps, but you can work through the algebra and confirm that, right? If you compare this to our first example for what the hip abductor force is, this is obviously a lot less. Right? And that's a direct result of the cane, not so much because of the weight that the cane is offloading, but more so just because it kind of helps correct your posture in a way. Okay. And so just kind of notice, think of both of those things going on. And so the cane is doing two things. Okay. So, the weight that the cane offloads, that's definitely important. And so, the fact that the hip joint is carrying less weight, of course, that's going to lead to less reaction forces there and less muscle forces. But the other important factor is the fact that, you don't have the center of mass just sitting right on top of your foot anymore. Then you have your leg is kind of more standing up straight. And so that'll help a lot more with these forces. Okay. Okay. And so let's take that result. Now that we have FM, we can go ahead and plug in for the joint reaction forces. Okay. So first we have JX. So JX is equal to FM cosine of 70 degrees. Okay. And so we plug in FM, we plug in cosine, we get 72.67 newtons. And then JY, we solve that equation for JY, we get W leg minus 200 newtons minus FM sine 30 or sine 70, excuse me. Okay. We plug it all in and we get a minus 350 newtons. Remember, getting negative forces is okay. So, if you get a negative reaction force, all it means is that the reaction force is in the opposite direction of what you pointed as. Okay. And so if you go back to our figure, our figure pointed the vertical component of the joint reaction in the positive y direction, pointing up. All this means is that it's just has a magnitude of 350 and it's pointing downwards instead. Okay, but it's no big deal. And so if you're doing your homework and you get if you get an answer that has either exactly the same or very similar magnitudes but opposite sign, all that means is that the force is just going in the opposite direction. And so you just probably drew it in an opposite direction than what I. Okay. All right. And so let's take the magnitude of this. Okay. And so if we take the magnitude, we just use the good old distance formula. Okay. Okay, so we take the square root of jx squared plus jy squared, and what we get is 357.46 newtons. So you can see from that, that's also a big reduction compared to before, in direct result of the cane, right? Any questions on this? Right. Okay, so that's the hip joint, and so a lot of really fascinating things happening there. Just doing normal everyday activities, just standing. So let's go ahead and move downwards. So let's talk about the knee joint now. And I think we have just enough time to do the knee joint example, and then we'll probably wrap it up for today. Okay. And so just like the hip joint, the knee joint is also responsible for weight bearing. Okay. Okay. And so because of the weight bearing responsibilities it has, but also due to the muscle activity around the knee typically experiences loads up to 3 to 4 times the body weight. And one thing I want you to remember that, remember that when your joint, the forces that your joints experience are not only due to the weights that's the weight that's there, but it's also due to the fact that the muscles are often acting to kind of push the joints, together as well. Okay? I think there's no joint that really exemplifies this more than the knee. Okay, so let's do an example. All right, and so we're going to do a static analysis of what's called a leg raise exercise. And so if you're familiar with the exercise, kind of imagine you're laying down on your bed, but your legs are kind of dangling over the edge. And so the leg raise exercise is just to kind of bring your legs up parallel with your body. Okay? So you're kind of laying in your bed, your legs are on the floor, and then you kind of bring it up, so it's parallel. Okay? All right, so it looks like this. Right, so let's say here's your thigh. This is your knee joint. Okay. So there is your lower leg. Here is your foot. Okay. And so let's say that you're doing this for exercise, and so you have maybe some ankle weights on your foot. Okay. And so we'll say that your foot has a weight W. We're going to have the weight of the leg. Okay, weight of the lower leg, we're going to assume is acting at the midpoint of the leg. Okay. This joint right here is your knee joint. And so we're going to be considering the joint reaction forces at the knee joint. And if we draw kind of the midline of the leg like that, we have a muscle force in red, a muscle force that kind of acts just like that. So the muscle force is going to be acting directly on the lower leg over the patella. Okay. And we're going to assume that FM here makes an angle of theta, with respect to the midline of the leg. Okay, and so just like before, there's a few more parameters that we have to add here, but I'll save it for the free body diagram. Okay. And so just like before, what we're interested in is computing the magnitude of the muscle force. Okay, so we're going to compute FM, as well as the joint reaction forces at the knee. So let's go ahead and draw the free body diagram. So I'm going to draw it a little bit bigger than the leg up there, just to make sure we can label everything. Okay. Okay. And so assume that we just zoomed in on the lower leg, or the lower leg grew into twice its length or something. Okay, so let's go ahead and put in all the weights that we saw. And so first thing we had was the weight of the leg, or excuse me, the weight at the end of the foot. Okay, so this can be W right here. And then we have the weight of the leg itself. And so we'll assume the weight of the leg is at the midpoint. Okay. And then we have the muscle force as well. So the muscle force, assume acts like that. Okay. And it has an attachment angle of theta m. Okay. And so be careful here. And so this is a little bit different than the last example, because in the last example, when we were given the angle for the muscle, it was with respect to the horizontal. Here, the angle that we're given is with respect to the leg shaft. Okay. And so it's going to affect our calculations a bit. And so, just kind of make sure you're aware of it. And so when you're doing homework problems and everything, don't just look at the angular values, but kind of look and see what that angle is defined relative to. Because otherwise, you're going to end up with some wrong answers. With that said, we do need an angle with respect to some kind of reference. And so what we'll assume here is that the leg itself is angled with respect to the horizontal by theta and leg. Okay, so theta leg will be that blue angle at the bottom. Okay. Next, we need the distances. Okay, so let's go ahead and label those. Okay, and all the distances will be relative to the leg shaft. Okay, so they're all going to be slanted. They're not going to be horizontal. Okay? And so here we have LM, and so LM will be the distance along the leg on which the muscle force acts. Okay. Next, we have the distance between the knee joint and the weight of the leg down the length of the leg, and so that's LL. And then finally, we have the length of the entire leg itself, which we'll call LW. And just like before, we're going to have the joint reaction forces, JX and JY. And so those are going to be acting at the knee joint. Okay. All right, so I think that's all the information that we need, save for the parameter values themselves, which I have on the next page for some reason. Okay, so let me go ahead and give you the values of all the parameters here. And so we'll say that LM here is 12 centimeters. LL here is 22 centimeters. LW is 50 centimeters. We have W leg. W leg here is 50 newtons. And we'll say the weight at the end of the leg is 150 newtons. So this person's really working out, and so he has massive ankle weights on, three times the weight of his own leg. And our angles here, we'll say that theta m will be 15 degrees, and theta leg will be 45 degrees. But we'll wait until the end to plug in the values. All right, and so just like before, let's go ahead and write out the equilibrium equations. Okay, so we're gonna have some of the forces in the x direction, some of the forces in the y direction, and some of the moments about the knee joint. Okay. All right, so some of the forces in the x direction, you know, we only have two of them here, and so it's gonna be jx. Okay. And jx, we pointed to the right, and so that's gonna be positive jx. Okay. Minus fm. And so we can see here that FM is pointed to up and to the left, and so we put a negative there. Okay. And since we want the horizontal component, we can do cosine. Now the question is, you know, what do we put for the angle here? And so, you know, I think, you know, if you're kind of following with kind of the previous examples, you know, you would just put theta m there and call it a day, right? But let me draw kind of a bigger picture of that just so you can see. Right? So we have the leg. We have FM. This right here is theta m. Remember, theta m is measured relative to the leg, whereas the leg makes an angle of theta leg with a horizontal, okay? Let me do this to make it a little bit more clear. And so, you know, we know that the leg, makes an angle 45 degrees with the horizontal, right? And so that means the entire leg is at that angle. So what I'm going to do is I'm going to move this up here. Okay. And so now you can kind of see, you know, the angle that we want here is not just theta m, it's going to be the sum of theta m and theta leg. Because remember, you know, we're summing up the forces in the horizontal x direction and the vertical y. Okay, and so the angles that we put in here have to be with respect to the horizontal x or the vertical y. Okay. And so that's why we add the two angles together, because that's the total angle with respect to horizontal. Okay? And so you have to be careful about that. And so I actually think one of the homework problems actually has some of this. And so you want to be careful with some of the angles that you're doing. Okay. All right, so now let's do the same for the y direction. So the y direction, we have a positive jy. We have the two weights, and so we have W leg minus W. Okay. Then we have the muscle force. And here we want the vertical component, and so we're going to have sine. And just like we did in the F equation, this is going to be sine of theta m plus theta leg. That's going to equal to 0. All right, and then finally, you know, we have the some of the moments around the knee. Okay, and so we're choosing the knee joint here because that's where our joint reaction forces are. And so, you know, if we sum the moments around them, around there, then you know we can solve for FM directly. Okay. Okay, so let's take a look. And remember, you know, the distances that we are given here, they're distances along the leg. And so that's going to factor into our calculations a little bit as well. Okay. So let's start with FM. Okay. Yes. Okay, so first we have FM. Okay. And if we draw kind of the vertical, whoops. And so if we draw the vertical and horizontal components here, remember theta m is defined relative to the leg, okay? And so the vertical component is going to go straight up, or not straight up, it's going to go perpendicular to the leg, whereas the horizontal component is going to go parallel to the leg. right? And so the only component of this force that's going to contribute to the moment is going to be the vertical one. Okay, and so we're going to have Fm sine of theta m, and then we're going to multiply it by the moment arm. And so that's going to be positive because it's going to do a counterclockwise moment around it. Okay. Next, we have W leg, right? And so W leg here is pointed straight down. Okay. And so the distance that we want is going to be this horizontal distance between W leg and the joint, right? And so this is the distance that we want for the moment arm. Okay. And so in the moment equation, we're going to define that as W leg LL cosine of theta leg. Okay. And so that LL cosine of theta leg, that's the horizontal distance between where W leg is acting and the knee joint. Okay. I'm gonna zoom out here just so I have enough room and you can see the figure above. Okay. Finally, we have the action of W, which is very similar. And so, you know, the distance that we want for this leg is given by this. Okay. Right. Because our force goes vertically downwards. And so, you know, the moment arm here is given by that horizontal distance. Okay. And so this is going to be minus W, LW, cosine of theta leg. Okay. But once again, this right here is the horizontal distance between W and the knee joint. All right. Any questions on how we obtain these equations here? Right. So definitely be careful with these cases where, you know, you want to make sure that you know kind of where the angles are being defined relative to, so you input it into your equilibrium equations correctly. Okay. So I think that's where a lot of people kind of get tripped up on these problems. Okay. Okay. So now that we have the equations defined here, it's just algebra. And so, you know, this is a pretty standard problem because we can take the moment equation and solve for Fm directly from this. Okay, so we get Fm is equal to W leg LL plus W LW times cosine of theta leg divided by LM sine theta m. Okay. You plug in the numbers for this, you get 1958 newtons. Okay. And so that is your muscle force. And so I should have mentioned before, so that muscle force is coming from your quadriceps muscle. So that's the muscle that's on the front of your thigh that kind of reaches over your kneecap and attaches to your lower leg. Okay. Okay. And so we're just about out of time, but I do want to mention something. Okay. And so we've mentioned this before, but you know, I want to talk a bit more about this term right here. In particular, you know, I want to talk about theta m. And so remember, theta m is the angle at which the muscle attaches to the bone. Okay. And I believe what we talked about last time was that the larger theta M is, you know, the less force the muscle has to exert. Okay? And that all has to do with this sine term right here, right? And so the extremes for the sine term are 0 and 90. And so the closer theta M is to 90, the less hard your muscle has to act, okay? The knee joint is very unique in that, you know, like I've just mentioned, the quadriceps muscle actually stretches right above your kneecap, okay? And so your knee joint actually kind of looks like this. And so you have your kneecap. Okay, so here's your patella. Okay? And so this right here, this is your tibia. And so the quadriceps muscle actually stretches right over the kneecap and attaches right there. Okay. Okay. For this angle right here, this angle is theta M. What's unique about this geometry is that, you know, if you notice what the patella is doing, what your kneecap is doing, it is basically kind of acting like a wedge. And so that wedge is kind of making it so the quadriceps has to go over that wedge to attach to your tibia. Okay? And the result of that is it actually helps to increase the attachment angle of the quadriceps. And so your patella actually plays quite an important role in kind of making sure that your quadriceps doesn't have to work as hard. Because the patella just, you know, makes sure, or it kind of increases theta M by kind of putting a wedge between the quadriceps and the tibia. Okay. And so even though the main role of the patella is to, you know, is to protect your knee, it also helps to kind of reduce the amount of load that your quadriceps muscle has to do. And so, you know, what scientists have seen is that for people with either a smaller patella, a smaller kneecap, or a removed kneecaps, their thigh muscles have to work a lot harder in order to kind of do the same motion as someone with a big kneecap. Okay. All right, any final questions on this? Okay, all right, and so that's all we got time for today. And so when we come back on Tuesday, we'll talk about some of the common injuries to the lower extremities, and then we'll start talking about the spine, okay? All right, and so thank you guys for coming in today. I know I went over time, so I thank you guys for your patience. I hope you guys have a great weekend. Take care of yourselves, and I'll see you guys next week. Yeah. Because it's actually on the right. So this needs it's going that's right here. And so it's actually pointing out here.
Yeah.
No, you work.
Oh, no.
It's just like.
All right, Sarah, any final questions on biomechanics? I know I'm going to see you for finite elements really soon. But...
No, I'm good. Thank you.
Okay, all right.